us this year, and yeah, hope to see you again soon. And without further ado, Paulo, take it away. Thank you.
Thank you. So, hi everyone. Quick question. Raise your hand if that's the first meetup you've been to where I am the presenter. Okay, most of you. Awesome. Just a couple of more show of hands so I can tailor the presentation to all of you. How many of you have never programmed in Java before? Raise your hand. Okay, one, two. Okay, cool. How many of you are new to AWS world? Okay, that's awesome. Okay, I think I can work with that. So my name is Paulo. I work at Atlassian. If you don't know the company name, that's fine. I work at a company that does Jira that some of you may not like because it brings you lots of strong feelings. I get it. You're not alone. Okay. But also we have other products, and I will talk a little bit about them in a shameless plug style. But it is my intention to entertain you for the next 30-ish minutes. I will talk about things that may be very complex. I plan to give you a crash course on anything that you need to know. But if you leave here today with a bunch of questions answered because I explained them properly, but with also a couple of acronyms or a couple of names of technologies that you never heard of, but you feel really curious that you need to go back home and Google them, for me, that's mission accomplished, right? Today we're going to talk about how Atlassian migrated Jira and Confluence to Graviton, but most importantly, about everything that went wrong. The last disclaimer is the following. Every story needs a villain and a hero. In that one, I sound like a hero because I fixed the problem. This is somewhat true, but not exactly the message. I was lucky to have other people that made all the mistakes, which is everything that went wrong, and so I could try something else. I would very easily have made the exact same mistakes. So I think that that's the bottom line. So shameless plug. This is the Atlassian cloud platform. You may know Jira, Confluence, and Loom, but we have definitely so many other products. As everything now needs to have a big thing. Rovo is our agentic AI product, which integrates with everything pretty much. Highly recommend that. I think it's really interesting. But today, topic is a little bit different. This is some of the customers that we basically make them happy a lot of times, not every time, and how we make this happen. So we have tens of thousands of EC2 instances. Even though we only have like a dozen public services, we have more than 3,000 internal services. For the majority of our products, we have a sharded architecture, which I will talk about a little bit in a second in case you're not familiar with that. But the most important information is we are available across 15 different AWS regions. So all the perks and problems that comes with it, we have it. For sharded architecture, just raise your hand. Have you ever worked with a sharded architecture before, or is this a new term for you? Okay, one, two, okay, easy. So the idea of having a sharded architecture is that instead of having a single application that is deployed and you just make it bigger and bigger and bigger to serve the requests of your customers, you have multiple smaller deployments of your application completely isolated from one another. So you have a few benefits. The first one is whenever you need to roll out new features, you can roll out to one of the shards, but not of all of the other ones. So in case that one goes wrong, you do not impact every single customer. So that's the main idea. Also, because the bigger your deployment is, you are more likely to hit certain limits. There are only so many connections you can make to the database. If you can't make it any higher, that number any higher, you need to actually duplicate your deployment. So that's roughly where it comes from. Now, it comes with very interesting challenges as well. The first one is for specific customers to hit one shard and other customers to hit another shard, there is a little magic, let's say, in the space, in the realm of network wizardry, because you have to route everything. So eventually you will have certain components which will be very critical, network being one of them. Also, and for me, that's the most interesting one, is if in a single shard, imagine this middle shard here, it doesn't have as many users as the other shards. So that means it's not being fully utilized as other shards, which can be translated in you wasting money without actually getting any profit for it. So as customers get bigger or smaller depending on their usage, you are forced to solve the problem of how to place them together in a way that they don't affect each other, which is not a deterministic science. There is a lot of heuristics and things like that, but it's something that will never be solved. It is in your best interest to have a little bit of fat in each one of those shards so you can accommodate spikes in traffic, but not so much so that you are just spending money, right? So very interesting problem, but it's the only way to scale at the level that we are right now. Let's talk about our Graviton attempts. So this, okay, just last show of hands. Is there anyone here that doesn't know what Graviton is? 1, 2, okay, awesome. So, the same people that raise their hands, you know what Intel is, right? Okay, cool. Intel is the company that manufacture types of computers, right? There are not only, there is not only Intel, there are other competitors in that space. There is one in particular called ARM. So ARM is a different type of architecture. And when I say architecture, I mean hardware architecture. And Graviton is the licensed model that AWS has with ARM. So they help design, the whole ship, the whole thing. Like it's basically their hardware in a way, but they license that with ARM, which is the manufacturer per se, like not the manufacturer, but the company that holds the intellectual property. The interesting point is, what are the differences and why do I care? So Intel essentially has the big monopoly and everything, but ARM has the unique selling point of saying we consume way less power for the exact same amount of instructions that you need to run. There are many interesting reasons why, not important for this topic, but you have to understand that over the years, the definition of performance changed. In the past was how many instructions you can run per second, and at some point we hit a limit because that's a physical limit, not an engineering limit. And then over time it was how many instructions you can run per kilowatt wasted to actually run those instructions. So it became some sort of a economy at scale type of problem. And ARM is the biggest competitor in that space. So Graviton is AWS answer to that problem. And their unique selling point for a long time was, if you move your application to Graviton, you will run with the same performance for X percent cheaper cost. So that was roughly their plan. This plan changed over time. I think right now they are not as cheap as Intel, but they have a higher performance, so you can consolidate the number of instances to still save money, right? But that's not the focus. The focus is, because in IT we only do things either because we can do things faster or because we can do things cheaper. Doing things cheaper is the reason why Atlassian wanted to move to Graviton. And at the time, we were running 2 instances in our fleet. So C6i, which is line 17, and C6A, which is line 21. On the right-hand side, I have a comparison of what's the closest Graviton instance and what would be the saving margin from that. So in the beginning, if we were only on C6I and we wanted to move to Graviton, we had a margin of 14% cost saving, which is great, because even if Graviton was 15% lower, it would kind of hit the break even. But as we moved to line 21, we only had a 5% margin. And that was part of the big problem, because we wanted to save 5% of our fleet, given that if you have tens of thousands of instances, that can represent millions of dollars, right? But you don't have a lot of margin for any sort of slowness in your application or in your migration per se. So what we tried at the time is keep it simple. Let's get something that works in Graviton. The same way that certain companies will try their product first before they make it available to other people. Atlassian has this concept called let's try Jira first. Why? Jira is the oldest application they have, and every single problem you can possibly imagine will happen in Jira. So if that works for Jira, it will definitely like for everything else, because we want to keep things standard. So the results I'm showing you right now are the results of Jira running in Intel and Graviton. And a couple of things that stand out here is that we saw not only that the runtime, which is the request time, was lower in Graviton, but also the query time. So it's like, oh, hang on, is the connection to the database lower as well? And that was actually part of the first problem I wanted you guys never to make. So if you have a question, instead of jumping into the problem and say, this is where the problem is, ask a bunch of other questions. Right now, in this moment, our team is split into two different focuses. One wanted to prove they had the confirmation bias that it has to be on database because this is what they knew. And the other team was like, no, this has to be on the web server because this is what they knew. And needless to say, none of them were right. But the most interesting part was these charts here. So what you will see at on the top row is the right moment in which we switch the traffic from Intel to Graviton. And you can see that the latency for the P90 or 90% of your traffic, or P99, which is 99% of your traffic, they both increased. So it's not like certain endpoints became slower while the others were kind of okay. All of them got slower. But if you see, the one at the bottom is very cryptic because latency increased, but the CPU utilization went down. And we're like, how do you explain that? Like, if the latency increased, it means that the maybe you don't have enough horsepower to crunch through all those instructions. So how come the CPU utilization went down? Maybe there is something blocking the execution of those instructions. And it is a reasonable guess. It's a wrong one, but it's a reasonable guess. So you get a team with lots of engineers, and that's what they thought. They dig into all the application traces. So that's the one you see from Grafana, a Grafana temple to be more precise. But the interesting thing is, at some point, someone found that on Intel, there was a specific routine that was consistent around, it was consistently executed around like 20 microseconds. But if you see that on Graviton, it varies a lot from 50 microseconds all the way to 4 milliseconds. And that variability was not only puzzling, but also it kind of led people to follow what was not the problem. Because if you get that routine in particular, you don't have to be an expert in Jira and everything, but if you used Jira in the past, you know that for every project that Jira has, you have different fields that you are forced to fill them out, otherwise you cannot create the task. But what it means is that Jira is one of the very few applications that let the user define what the data schema or the database schema is for that project, which means that something that cannot be fully optimized. So you get a CPU. The way CPU got faster over time and they abide by the Moore's law and everything is not only by the density of transistors, but also because we leverage lots of hacks. Some of those hacks is right now CPUs depend heavily on speculation. That speculation is the ability of figuring out what the next instruction is going to be. So it tries to fetch the next instruction. And when it misses it, then your CPU runs lower. When it gets it right, it runs as fast as it could. Now, Jira cannot be optimized to that level to really use speculation because you are letting your customer define what the database scheme is going to be. How do you fully optimize for that? Now, when people saw this, they dug into flame charts or flame graphs. Essentially is a chart that represents how much time on which fraction of your application and operating system the CPU is wasting time, and they wasted weeks looking at that. And you can waste even more. But the problem is, this is a tracing, this is a profiling mechanism. You can only see what you're asking to see, but there is a trap. If you're trying to measure something, you're essentially saying, look, CPU, don't run the code I'm asking you to run. Run these particular instructions here, which is the instrumentation, that will actually let your code be do the accounting and do essentially everything that it needs to do to give you the answer of this is how many times a certain instruction was executed, and only then is that it executes the instruction. So trying to measure something skews the result of what you're trying to measure. So this is one good example of why. We can see the chart, we can click on each one of those things, but does it actually answers the question of what is running slower? And the answer is no. Multiple teams tried to look at that, they couldn't find it. There was a team that actually found this. So this is a service called AWS Code Guru. It does continuous profiling. So essentially it will try to answer some of those questions of how much time a specific task was spending on CPU, or how much time it was blocked and things like that. But it's a continuous profiling. So if you get lucky and your request is the one being traced, maybe you can find something meaningful. A lot of times it may not be traced. So if that's representative in terms of all of your requests, that's a good tool to use. For what we're trying to see, it was like trying to find a needle in a haystack. But interestingly enough, if you look at this particular line, you may not see from if you are really far away from the projector, but there is a method called isEditable. The most important part is someone noticed that if you see the legend at the bottom, that this particular method was spending a lot of time blocked, and people were like, why? And they eventually decided to do a deeper analysis at the operating system level, and they realized that between Linux running on Intel and Linux running on Graviton, there were certain system calls or certain operations for doing locking that runs lower on Graviton. At least that was the perception. I'm just kind of highlighting, the difference here. And that led them to find a particular piece of lock, not super interesting what it does, but the most important part is there is the synchronized line on line number 7. It basically locks all the threads that are trying to access that variable. So if you have multiple CPUs running threads and they all point to the same variable, all of the other CPUs have to wait until this lock is given up. So after that, they can run what they were running. So this would explain what we saw on the previous chart. So there were some improvements that came out of it. It didn't do the trick, but that investigation line sort of helped. Now, the problem remained the same. What is actually wrong? So we found some source of slowness, but fixing them didn't bridge the gap between the performance we found in Graviton and the performance we found in Intel. And the biggest problem was the slowness was perceived to be anywhere and everywhere. And that's the performance engineer's nightmare. Because like, well, what do you do next, right? Rewriting large pieces of code is not an option, at least not in Jira, because you have to account not only for your desire as an engineer of getting things right, but there are other aspects that needs to be factored in. So the first one is Jira has more than 1 million lines of code. Try to do that, you're going to spend a lot of time. And by the time you start thinking about it, you're like, hang on, how do I make sure that whatever I rewrite is actually correct from a logical point of view? Because just having tests is good. You can have a 100% line coverability. That means your test is touching every one of those lines. But does that mean you're testing every single possibility of what could be executed by those lines? And usually the answer is no. Like, a high number of testing is good, but it doesn't give you the confidence level you actually need to change critical pieces of code. The other thing is, if you talk about rewriting code, you have to factor how much time you're going to spend rewriting the code and translate that into money and see if that's going to compensate for how much money you're saving, right? In the long run, kind of makes sense, but try to convince a business that has short-term goals. That's a much harder conversation to be had. Last but not least, we have committed items in our public roadmap. It's not like we can, give up on them. Okay, with that out of the way, our best suggestion of what was wrong is there is something wrong in the operating system that runs lower in Graviton. It's really, between quotes, the best because we didn't have anything else we could show for. Now, this is where things really went tough. So at some point, the head of engineering came to us and said, okay, you guys spend far too many days trying to do the migration to Graviton. We can't do this anymore. Go back to project work. So Graviton is off limits for now. But most importantly, if we ever want to try this again, I have to have a reproducible and unquestionable evidence of why it couldn't run before and what makes it run now. And at this point, you see that the problem is no longer technical. There is a problem of distrust, like maybe the SRE team is not able to troubleshoot where things are going wrong. And some people will have existential crisis in moments like that. Other people will get upset, but that was the moment I joined the company. So they hired me, after this quote was, was said. So in September 2024, I actually joined the company. It was actually in September 2024. So Graviton 4 was launched. AWS claimed that it would deliver 30% better performance over Graviton 3 based instances. We were skeptical, not because we don't trust AWS, far from it, that's not the case. It's because it didn't do the trick for us before. So we're like, we cannot make a mistake once again. Like, are you really sure that that's going to bridge the gap? As I mentioned, it was just a moment I joined the company back then. And the things I had to work with was simply saying that it runs faster on Graviton 4 wouldn't do the trick because I had to explain why it couldn't run on Graviton 3 first. So it was a tricky situation. And like I said, faith in Graviton wasn't the best, so new attempts were perceived as a risk first, and only them as a cost-saving opportunity. And this is something that a lot of people don't realize. So trust is risk, and risk aversion is the name in business, is the name of the game in business. Like, you have to convince people that they should trust you, right? Because of that, and because all of the other mistakes that have been made before, we wanted to approach this differently this time. So the first thing is no passive benchmarking was to be conducted. So passive benchmarking is when you simply change the instance type and you throw a bunch of requests at it, and then you get the results. And if they are good, awesome. If they are not, you still don't know what happened, which is pretty much what we did in the beginning. So the problem is, if you are lucky and every single aspect of the new architecture is better than the one before, awesome. There is nothing else to be explained. But this is usually not how things go. Like maybe some operations will be faster. Maybe some operations are going to be slower. And then you're going to start, having questions like, if the results are good, have I really reproduced the volume of requests that a shard in production would have? And if the results are bad, like, is this traffic really representative of what we have in production? Because not all endpoints are requested in the same proportion. Like, do I have to replay the traffic in production but into this isolated environment? And if you think that that's a good idea, I have bad news for you as well. Because if you're dealing with traffic production that you want to replay, that involves personal identifiable information, security team is not going to like you. There are many, many hops you have to jump. So still, not all of them are good ideas, but we wanted to make sure that this is not the mistake we want to make again. The second thing is, I truly believe that the mistake we made in the first attempt is that we jumped into the optimization mode too soon. Micro benchmarking is like when you have a small piece of code that runs slower, then you try that piece of code and you try to measure it, and you try variations of writing that piece of code until you get the one that's the fastest. That's awesome. When you try to do micro benchmarking on something that has 1 million lines of code, you're not gonna get the answer you're looking for. So in our approach this time, we thought, let's find something that is unquestionable that this might be the bottleneck, and only then we investigate that bottleneck first. Like, we're not going to jump into the source code because rewriting is not an option. The rule number 3, and I think that was one of the most important ones, we defined what good numbers are. So here's the thing that in hindsight sounds obvious, but is not that obvious when you're trying to fix that problem yourself. If you get a machine and you overload all the resource of that machine in one go, everything in that machine is going to misbehave. How can you tell apart what is the symptom from what's the cause? You really can't. Everything is misbehaving because the system is trying to keep up, essentially. So there is one technique which is called finding the breaking latency, which is at some point you start increase the number of requests gradually that you send to that particular machine, and you will see that at some very specific number, the latency grows exponentially. That's when you really hit the bottleneck, whatever the bottleneck is. After you get that number, you run the test again, and you do the exact same experiment, but just a few requests before the bottleneck is actually, goes haywire. So that is more likely to give you the idea of what's the signal instead of just showing you all the noise. The other thing we did specifically for this is, instead of testing all the endpoints, we want to find one endpoint that touches the majority of our core experience in our code base. We have 1 million lines of code, and we want to know what's the SLO we have to abide by. So if the latency cannot go beyond 500 milliseconds, that's the number we have to work with. That number is hypothetical, by the way, but I will work with whatever I can before it goes beyond 500 milliseconds of latency. So I think that's the rough idea. It will be good in a second, I promise. Now, the last thing is, I'm not sure if that was obvious when I showed you all of the previous problems, but some people were trying to find problems in the source code because they were developers. Some people trying to find the problems in the database because they are database engineers. And some people are trying to find problems in the operating system because they are Linux experts. So that's confirmation bias in a way. Because no one could actually point to a single direction, I told them, like, hey, let's actually capture hardware performance metrics, but instead of instrumenting the source code so we can get those answers, which would skew the results, we're going to use the functionality of a hardware that actually does that and does not require changing your source code. So the overhead of capturing that data is as low as it can possibly be. The name of this is called Performance Monitoring Unit. I'm going to give you a crash course in a second, so don't worry about that. But the most important part is right now we're not only capturing the application metrics and the OS metrics, but also the hardware metrics, and try to compare that with Graviton. Now, what you need to know about PMU. So performance units are events used to measure CPU performance at a low level with low overhead. It basically gives you an understanding of what the CPU is doing at any point in time. Because we know CPU is a big black box. It is a big calculator, but there are many components inside of it, and each one of them is even more important than the next. So it's a way of actually breaking that apart without having to know intellectual property of that particular manufacturer. Needless to say, every CPU manufacturer does that differently. They don't have the same metrics, but the mechanism is roughly the same. So it's something that you can always count is going to be available, even though they have different names. The PMU 202 course is in Linux. The way you get those metrics is by using a utility called perf. I'm drawing like a couple of arrows in places that I believe it might be interesting. You don't have to know all of them, but just some of them that might be relevant. So CPU is not a single thing. It does have a front end and back end, even though it has nothing to do with JavaScript and back end as a a programming language as a whole. But the front end of a CPU is the part that checks whether a particular memory address is in cache or not. It does the decoding of the instruction that needs to be executed and so on. The back end of a CPU is the part that actually does the the calculation, the data crunching per se. So if the front end is overloaded but the back end is not overloaded, you're gonna see the CPU utilization low, but in a way it's pointing you to some sort of bottleneck, right? The other thing which is relevant here is the two arrows at the bottom. So we perceive programming logic, specifically when you have if statements, as like a big tree of decisions. Like, wow, if this happens, if true, go here, if no, go that way. In practice, it's not how it works. Your compiler has to put them one on top of each other. And as I mentioned before, CPUs rely heavily on speculation. So if you have an if statement and the branch, like the true or false or the then or else of your if statement is actually the next instruction, which was already prefetched, so it's speculated, then it runs as fast as possible. So that's a branch. But if your computer or your CPU has to jump into another part of your code because that was not the part that was speculated, that's a branch miss. So it runs slower. In certain programming languages, you are able to tell the compiler, like, even though visually it makes sense to write this way, I want you to switch the if and else. So you give the CPU a chance of optimizing for the majority of use cases. In other programming languages, you have to rewrite the way you initially wrote your code for that to happen. And other programming languages, you're not even given a choice. Java is one of them, by the way. So this is the type, not all, but this is the type of information I wanted to fetch from that experiment. And we finally found the culprits. Now, you may have realized I love to give people crash courses. There is one more. Last one, I promise. Because if I don't give you this crash course, you're not going to understand the finding. So let's talk about CPUs. So the big gray box is what a CPU represents. And inside of a CPU, you're going to have multiple cores, right? The most important part here is your CPU have no idea of anything else apart from memory and cache. So memory is what we are taught when we've gone to university, that this is the fastest way of actually fetching data. It's not. CPU has a cache, and what it does is the following. Layer 1 cache is very small, and it's local to every specific core, but it's the fastest one. Like there is nothing that could be faster on a CPU core. Layer 2 is slightly bigger, not as fast as layer 1, but it does the job. When layer 1 doesn't have the data, layer 2 doesn't have the data, then the core, before it goes to the main memory and fetch that information, it tries layer 3. This changes from motherboard and CPU manufacturer from one from another, but layer 3 cache, even though it's faster than memory, it tends to be shared across multiple cores, okay? The interesting thing is, there are very unique edge cases that you may need to think about. For instance, layer 3 cache is the biggest cache, but is not as big as main memory. So if your source of code needs to fetch some data from main memory and layer 3 cache is full, you need to drop something. And if the next instruction actually needs that information that you just dropped, you need to go to the main memory again, drop something else, and put it back. Clearly, there are lots of heuristics and smarts built into it, but this mechanism of actually dropping and pulling data out of memory in a cycle, some people call it as cache trashing, okay? So that's the most common case. There is another common case which was the problem for us. If you are compiling something and you put that in layer 3 cache, and that's awesome. But then as that particular piece of code gets more and more used, the CPU core will try to pull that from layer 3 into layer 2 because that's faster than layer 3. But layer 2 cache is smaller. If that does not fit in layer 2, it will drop from layer 3 as well because it simply cannot be promoted. This is interesting and very debatable because it depends on the design that the CPU manufacturer has implemented and everything. But we all can agree that it is in your best interest that your code leverages all the 3 levels of cache to the maximum, and going to the memory should be the exception rather than the rule. Do we all agree with that so far? Awesome. This is the chart that we got. Requires a little bit of explanation, but layer 3, now you know what it is. MPKI means misprediction per kilo instruction. Essentially is, you're trying to find something in L3, it could not be found, the CPU needed to go to the main memory to fetch it. If you see the top one, per 1,000 instructions, we had a baseline of between 10 to 15 misprediction instructions. If you go to Graviton, and that's Graviton 3, this baseline was much beyond 20, and sometimes it would peak all the way to 50 or 40. That is a more consistent and reproducible way of explaining why we saw the variability of why those particular functions would be so much more stable in Intel, but it would vary a lot in Graviton. So that gives a good explanation why. Now, we found a difference. Now we need to fix it. Like what we have at our disposal, because changing the source code is not one, and Java does not let you actually optimize the source code so much. The JVM does most of the job, which is a beauty and a curse at the same time. Now, the first thing you can do is because there was someone here that raised their hand when I said, hey, raise your hand if you never worked with Java before. Just a little bit of an introduction. Java is a compiled and interpreted language. So you write in Java and generates an intermediate code. And then the Java virtual machine is another program that reads that and executes it in your operating system. So that's what makes it operating system agnostic, right? Now, reading something and trying to interpret it on the fly will always be slower than a compiled program which is purposely built for that particular architecture and operating system. And Java developers knew that back in the day. So to bridge the performance gap, they implemented something called just-in-time compilation, which is JIT. Basically what it does is it tries to profile pieces of code that is frequently executed and compile that to machine code on the fly. And it's great. It bridged a lot of the gap, of performance. Now, there is some misunderstanding that people have about it. The first one is people believe that because just-in-time compiler make things faster, if I give it a lot of space, it will make more things faster. So my application is going to run even faster. This is not true. It sounds intuitive, but it's not true. What the just-in-time compiler will do is, if it can see a big space, it will try to compile big things. But layer 3 cache has a size, layer 2 cache has a smaller size, and layer 1 has an even smaller one. So actually, restraining the amount of space that your just-in-time compiler has available will force it to be more picky about what to compile. And if they can better leverage the CPU cache, that's where you're going to get the performance boost. So the levers you have at your disposal are these two parameters, initial code size and reserved code cache size. If you leave today with this particular information as a takeaway, in 90% of the cases, a reserved code cache size of 64 megabytes all the way to 128 megabytes is usually what you need for most applications, regardless of the size. You're gold. Like, my mission is accomplished in a way. Like, I feel really happy. Just for reference, when I saw this at Atlassian, they were using 1.5 gigabytes of cache. That was really, really wrong. Like, I wanted to strangle someone for a second. Like, I couldn't, because that's a professional environment, but I wanted, really wanted. Now, there is another thing we have to do. The compilation between Java code to machine code needs to run on a processor, because that's what the CPU does, right? But it cannot run all the time, because if you're running the optimization bit, you are wasting time that could be used to serve user requests. So you need to make the just-in-time compiler smarter, that it doesn't spend more time compiling something than to actually executing it. The levers you have available, and right now, it's enabled by default, so you actually don't have to do anything, but please don't disable it. I think that's the bottom line, is to use this particular parameter here. It's called tiered compilation. The short version of it is the following. There are two compilers. One is called C1 and C2. The C1 will get the interpreted code and generate a machine code which is not fully optimized, but is faster than the interpreted one, but it doesn't waste a lot of cycles. And then the JVM will keep profiling that piece of code, and when it thinks it actually needs to profile even more, then it uses the C2 compiler, which produces highly optimized code. So you don't have to change anything in your Java programming thing, source code, but just understanding, how this whole dynamic works is sufficient for now. Cool. Now, this solved part of the problem, but I could not afford the luxury of not finding a way of making Jira run faster on Graviton 3. So, as a card up my sleeve, I said, My background is in low-level development. I know a couple of things that can make stuff faster without changing source code. I might as well just use it now. And this is something that I believe it might be a good takeaway as well. If you have I'm not going to say just Java, but Java is for sure. But if you have a web application running Linux, if you use this, 9 out of 10 times it will make your application between 8 and 12% faster. It's very simple. DBAs know this, but developers don't for some reason. So this is the thing that got me the idea. So TOB table walk, and that's a terrible name. It may mean absolutely nothing to you. I will tell you everything you need to know again. Here's the thing. Your CPU doesn't know anything but memory. So if you have a variable, that's a memory address to your CPU. If you're trying to access a file, it's a memory address to your CPU as well. It's just the way the whole mapping thing works. Now, your program and my program needs to be running on the same machine. And I do not know which variable addresses you're using. So the trick that operating systems use is it creates literally a random address for you, but the operating system will translate that on the fly without you having to do anything into the actual physical address. So if you and I use the same virtual address, I will be pointing to a different physical location than you are. Okay, that's the rough idea. Now, this translation needs to happen somewhere. The CPU has a specific chip that does that. It's called MMU. Don't worry too much about it, but it's a microcontroller that does exactly that. But that requires going to the memory in Intel 5 times, in Graviton 4 times. So the thing that's actually slower is going to the memory 4 times for actually converting virtual address to physical address. And CPU manufacturers know this. The way they bridged the gap is by creating another cache layer. It's called TOB. That's what TOB is. It's just another fancy name for cache. When you actually have to go to the memory multiple times to convert the virtual address to physical address, that's what people call table lock, because they are organized in multiple tables. Anyway, the important part is every page in your operating system has the size of a 4 kilobyte, unless you say otherwise. This has been in an industry standard for 30 to 40 years or even more. I don't think that's going to change, right? Now, when Jira runs on very big machines, like 16 gigabytes of memory, if you have lots of those translations, every single 4 kilobyte page needs to be translated and put into the cache. The cache is also not big. So as you're translating things that were not in the cache, you're dropping something else. And then you have to go to the memory multiple times once again. So one way of solving that problem is, what if I could tell the operating system, instead of using 4 kilobyte pages, what if you use a 1 gigabyte page? Like surely all the translations are going to fit into the cache, and I will never go to the memory 4 times in a row once again. This is called transparent huge pages. So DBAs love it because databases like Oracle, Postgres, they rely on this to keep the performance up. So it's precisely what I described. In Java, all you have to do is use this particular parameter called use transparent huge pages. You may need to enable something on your Linux kernel, but that's something very simple. You can find this online. You wouldn't fit in this slide, but it does exactly what I said. So if I only need 15 slots to do the virtual to physical address translation, they all fit the cache, happy days. And this is the results you can see. So the first one is a Graviton instance, a very old generation. And for 1,000 instructions, it was doing the table log 0.8 or 80% of the time. For Graviton 3, when I enable transparent huge pages, GHP, it went down to 0.10. That's a big jump. For Graviton 4, it was 0.06. So there was almost no table log here. Now, here comes the best part, the results. This is what you're waiting for. Then again, so Intel baseline is the one, the first one on the left. I also applied, for fairness, I applied the transparent huge pages to Intel, and you could see that the latency of our endpoint reduced from 350 milliseconds to 330 milliseconds. So I could use that for Intel. I didn't because I wanted to move to Graviton. For Graviton 3, with the improvements we've made to the JVM, but without the transparent huge pages, we got it down to 393 milliseconds, which is a big bump. If you recall when we did the cutover from Intel to Graviton, it went all the way to 450, 500 milliseconds. Now it's pretty much stable with beneath 400 milliseconds. When I enabled transparent huge pages, it went down to 360 milliseconds. So now I only have a 3% difference between Intel and Graviton, considering that we could save 5%. So if you subtract one thing by another, I was saving 2% for the entire company of tens of thousands of instances. So that was good enough. But then at that time, Graviton 4 was already a thing. So we ran in Graviton 4 with the optimizations and everything. It was 22% faster. And when I used the transparent huge pages, it went to 233 milliseconds, which was like 33% faster, even beyond the claim that AWS had in their product page. Now, cool. So we solved the problem. Good days, right? Happy days. We can all go home, right? Things can always get worse, right? I mean, you can see by my accent, I'm from South America. I love a little bit of drama, okay? Here's the thing. Atlassian has been in the cloud business for a long time. What is common for us might be uncommon for you guys or rare for you guys. So when you try to launch an instance in a specific data center, a specific availability zone, and that instance type is not available, you get an error that is famously known as ICE, insufficient capacity error. We get between 10 to 15,000 ICE errors per hour. That's a lot. But that has taught a lot of things for us. This is not a fault on AWS at all. I just want to make this clear. It's just like we demand a lot of instances, and instances, they have finite numbers, right? So the one thing that eventually became norm for us is we launch an instance, but if we don't get this one, we try something else. And if we got that one, we try something else. But here's the problem. We were on Intel, and now we're trying to go to Graviton. Graviton 4 is new. We're definitely going to get ICE errors because it's not even available in every single region. Graviton 3 is great. It has a slightly lower performance, but we could compensate financially wise. That's awesome. But it's still, what if I don't get Graviton 3? What do I do? Because if you recall, if you use a auto-scaling group, you create a launch template. A launch template was the AMI, which is your machine image. That one is architecture specific. If I'm using Graviton 3 and nothing else works for me, what's the other ARM instance type that I can use? Like I don't have an option, and I suffered 10,000. I received 10,000 ICE errors per hour. So we needed to find a way around it. So AWS has a solution for that. It's called a auto-scaling group multi-arch template. Slightly more complicated than it should be, but it works beautifully. So essentially, when you create your auto-scaling group, you specify that you have a mixed instance policies and everything, and you just say the following, like my default template is this one at the top, which is the one for Intel. And at the bottom, you're saying what are the instance types for Intel that you're interested in. And the one at the bottom is also override that with my launch template for ARM. And these are the instance types I care about ARM. In practice, depending on the order you do those things, you're establishing sort of a priority order that you want the EC2 control plane to launch instances for you. Like I want first Graviton 4, then Graviton 3. If you cannot find any of them, please give me this Intel one, which I know works. So that's roughly how we did. if you were to picture this, that's exactly what I just described. Now, this is probably the interesting one. So by the time we actually went through the rollout process, there were a lot more Graviton 4 instances available. We worked really closely with our account team to get them available to us. But you could see that we hit the limit of Graviton 4 in all of them. So yellow instances are Graviton 4, blue instances are Graviton 3, and pink instances are Intel. In all of those cases around the globe, we actually had all three at the same time. So it was a good thing that we actually got worried about ice errors and everything. So our baseline is around 2.5, 3,000 instances, but depending on the moment we go up all the way to 5,000 instances for Jira. And then we did the exact same thing for Confluence, but we knew the answer, which was much easier. It only took like a couple of weeks. But